we're going to try out this smart board today, see how it works, see what you guys think. But we are going to talk about section 7.6 today, which is talking about the rational zero theorem. Okay, the rational zero theorem says that if f of x is this long polynomial, basically all these letters just mean that you have some degree with a coefficient going all the way down to a constant. So if you have a polynomial like this that represents a polynomial of integral coefficients, then if p over q is a rational zero in simplest form of f of x, so if you have some sort of fraction or number that's reduced fullest, then p, or your numerator, is going to be a factor of an, and q is going to be a factor of a naught. That should be a naught. Okay, so q goes with this one, and then our p goes with our constant at the end. Okay? So for example here, if we have this polynomial, 2x cubed plus 3x squared minus 17x plus 12, okay? And we're given that 3 halves is a 0, then we can see here that 3 is a factor of 12. So 3 is a factor of this constant, and 2 is a factor of 2. Okay? We are going to use this theorem sort of in reverse to help us when we want to find zeros given a polynomial. Okay? So what we can say here is if we have some sort of polynomial, we know that possible rational zeros are going to be factors of a to the n of your constant over factors of the leading coefficient. Okay? So, we want to list all possible rational zeros of the following functions. Again, we don't have something that's for sure, so Descartes' rule of signs gave us a hint of how many positive or how many negative or imaginary zeros we're going to have. The rational zero theorem is going to give us possible numbers that we can try, but it's going to be sort of trial and error as to which one's going to work. Okay? So here, if we want to list all possible rational zeros of the following functions, we have this polynomial, x to the 4th plus 7x cubed minus 2x squared plus x minus 15. Okay? Our rational zero theorem said if we have p over q, then p is a factor of our constant, and q is going to be a factor of our leading coefficient. Okay? So our constant here is 15. And then our constant here, our leading coefficient, is 1. Okay, now we have to list factors of these. And as you list factors, you want to take into account the positive and negatives of both. So with 15, to get 15, we can either have 1 times 15, so plus or minus 1 plus or minus 15. I'm going to come out there. So 15 is plus or minus 1 plus or minus 15. We can also have plus or minus 3, plus or minus 5. Now, why are we including a plus or minus? Because if I have negative 1 times negative 15, it gets me 15. If I have positive 1 times positive 15, it gets me 15. So you want to take into consideration all of the possibilities, including those negatives. Okay? And our possibilities here for 1 are just plus or minus 1. Okay? So if we want to find all possible rational zeros of the following function, we would take our factors of our constant, which is our p, and these guys, and divide them all by every single possible factor of q. Here our factors are 1, so if we divide everything by plus or minus 1, you don't have to do this, I'm just showing you what we're doing. Okay, our possible factors are plus or minus 1, or possible zeros, excuse me, plus or minus 15, plus or minus 3, plus or minus 5. Okay, those are our all possible rational zeros. Okay, so we have essentially narrowed down the field of some sort of rational zero from infinite possibilities down to 8. Okay, so our chances of finding a rational zero by just guessing and checking are now a lot better because we've been able to use this theorem to help us narrow our search. Okay? Another example, here we have f of x equals 3 which here is 4. That's our constant. And then our q is our leading coefficient, which here our biggest degree is 4, so our leading coefficient is going to be 3. Okay, so factors of 4, we have plus or minus 1, plus or minus 4, and we also have plus or minus 2. Factors of 3, we have plus or minus 1, plus or minus 3. Okay, to find possible rational zeros of the following functions, what we're going to have to do is we're going to have to take all possibilities of p's divided by q. Okay, so we're going to take every single p here and divide it by this q. So if we take all these and divide it by 1, we're going to get plus or minus 1, plus or minus 4, plus or minus 2. Okay? Check. Now we're going to take all these and divide by this q, which is 3. So if we take 1 divided by 3, we're going to get plus or minus 1/3. If we take 4 divided by 3, we're going to have plus or minus 4/3. And if we take 2 divided by 3, we're going to get plus or minus 2/3. Okay, so now these are all possible zeros. Okay, so when you have more than one factor for q, you're going to get a little bit more. Sometimes you might duplicate, but just don't count the duplications. But here, we have to make sure that we divide all of our p's by all of our q's. Okay? Line up your q's. Alright. Now our example says that we need to find all zeros. Okay, so what we're going to do is we're going to use the rational zero theorem to help us figure out which zeros are possible. Okay, so we're going to start with our p and q, which our p here is going to be 60, and our q is 2. Okay, so possible factors of 60, we have plus or minus 1, plus or minus 60, we have 2 and 30, we have 3, plus or minus 3, and 20, 4 does not work, 5, and 12, 6, and 10. Ooh, that's a lot. Okay, and then 2, we have plus or minus 1, plus or minus 2. Okay, so if I'm going to take all of my p's and divide them by all of my q's, right now what I'm going to do is I'm going to take all of these and divide them all by 1, which means I'm going to have this list of two numbers, because all of these divided by 1 are the same thing. So now I'm going to go through and divide everything by 2 and see if there's anything I can add to this list. Okay, so this is going to be my running list, and I'm just going to add things to it. So I'm going to have 1 divided by 2, which is going to give me plus or minus 1/2. I'm going to have 60 divided by 2, which is 30, and 30 is already in my list, so I don't have to worry about it. 2 divided by 2 is 1. 30 divided by 2 is 15. I need to add that one. Did I forget that one? Is that 4? Nope, we forgot some. Plus or minus 4, plus or minus 15. 3 divided by 2 is 3/2. 20 divided by 2 is 10, which we already have. 5 divided by 2 is 5/2. 12 divided by 2 is 6. 6 divided by 2 is 3. 10 divided by 2 is 5. Okay, so those are all of our possibilities. Okay? Now, it may look daunting, but the fact of the matter is that we have narrowed this down from an infinite number down to just these. Okay, so it's actually quite a small percentage that we've eliminated to. Okay, and now, here comes the fun part. In order to find all the zeros, we're going to use synthetic division, which is going to be using our factor theorem. So we're going to synthetically divide some of these roots into this polynomial and see which ones have a remainder of 0, because then we know they're factors. Now this is going to be strictly guess and check. Okay? There's no rhyme or reason. We can use Descartes' rule of signs to see if we have any positive or negative ones. But really this is just going to be guess and check. So you're going to go from there. Okay? So, to set up our synthetic division, I'm going to have my roots here, and I'm going to bring down my coefficients. 2, -13, 23, -52, and usually do a shorthand of synthetic division, so I'm going to be able to try a bunch of roots. I'm going to try 2, 3, and 5. Okay, I'm just going to line up my roots here. So it's like I'm doing 3 synthetic division problems at once. So my first step is I'm going to drop it like a tot, so I drop the 2's all down. Okay, and now we go through our process. Multiply and then add. Multiply, then add. So 2 times 2 is 4. 4 plus 13, negative 13, excuse me, is negative 9. Negative 9 times 2 is negative 18. Negative 18 plus 23 is 5. 5 times 2 is 10. Negative 52 and 10 is negative 42. Negative 42 and negative 2 is negative 84, which is not 0. Okay, so that one doesn't work. So we're not using 2. So let's try 3. 2 times 3 is 6. 6 plus negative 13 is negative 7. Negative 7 times 3 is negative 21. Plus 23 is 2. 2 times 3 is 6. 6 plus negative 52 is negative 46. Yeah. Negative 46 times 3 is going to be very large. When you add that to 60, it's not going to be 0. So 3 doesn't work. So now let's try 5. 2 times 5 is 10. 10 plus negative 13 is negative 3. Negative 3 times 5 is negative 15. Negative 15 plus 23 is 8. 8 and 5 is 40. Plus 52 is negative 12. Negative 12 and 5 is negative 60, which gives us a 0 here, meaning that 5 is a 0. Hooray! Okay? From here, we are not done because we're asked to find all the zeros. So we have found 1 0, which is 5. Okay? Now what we can do is we can pick another one, pick some more, and just keep dividing them out to see if we can get. Or what we can do is factor. Both ways are fine. Okay? If we choose to factor, notice that here we're going to have nothing, an x, x squared, x cubed. So we're going to have 2x cubed minus 3x plus 8x minus 12. Okay, what can we do from here? We can factor by grouping. Okay, so here these two share an x squared, which is going to leave me with 2x minus 3. And then these two share a positive 4, and that's going to leave me with 2x minus 3. So factor by grouping, these both share a 2x minus 3, leaving me with x squared plus 4. Okay? It asks for the zeros, so I'm going to use my zero product property. I'm going to take 2x minus 3 and set that equal to 0 and solve. So another 0 that we have is 3 halves. And then I'm going to take x squared minus 4 equals 0. Or, excuse me, plus 4. So I'm going to subtract 4. X squared equals negative 4 if I take a square root. X equals plus or minus, over here plus or minus, 2i. Okay, so we have a 4th degree, which means we're going to have 4 roots, and our roots are x equals, the first one we found was 5, the second one we found was 3 halves, and then we also found plus or minus 2i. Okay? And that is rational root theorem.